Welcome back everyone. It is 2023, a brand new year with a lot of opportunities to learn, to create and to just enjoy the little things in life. Today we will be looking at carbon fiber machining. Yes, carbon fiber is a very machinable product, can be machined into very useful shapes. There's quite a few precautions that you have to take that is very necessary for your health and your safety. When machining carbon fiber, it is not something that you want to inhale
or get into your lungs
or really touch in its powder form. We're going to look at the different precautions that we take when we machine the product. We are going to design a little part in Fusion 360, which is the CAD/CAM program that I use. For anyone that is interested in CAD/CAM design, I can highly recommend Fusion 360. It is a free program that helps you as a hobbyist, as a beginner machinist to get engaged in the world of CAD and CAM. It has a lot of functionalities included in the free version. There is a paid version. The free version is full of really useful things. I used the free version for a very long time before I felt the need to go over to the paid version. We are going to look at Mach 3 a little bit. I'm not ever going to do an in-depth overview on the Mach 3 control system for CNC machines. And the reason for that is I'm not a particularly big fan of the system. I am going to move away from it to either a Meso G3 touch system or a Acorn Centroid system. I've not quite decided yet which one of the two. They have a lot of amazing features, each have their pros and their cons. I still have to decide on that. We are going to design a part for the little 10th scale carbon fiber car and get it one step closer to running 300 kilometers per hour. Okay, so we're going to do CAD/CAM, we're going to do a bit of CNC work, and we're going to look at the little RC car that needs to fly to the moon. Join me on this journey. Okay, welcome to Fusion 360. I'm not going to do a deep dive on Fusion at this point. This is the CAD/CAM program that I use. What I love about this most is that you can seamlessly switch from the design page on the top left here into the manufacturing workspace, which takes you directly from your drawing to your milling, turning, additive, fabrication work. And I really love that. So the little project that I have here is this Savox micro Savox servo adapter. Okay, so this is the little part that we are going to look at. I use a 3D connection space mouse for my CAD/CAM work, and I absolutely love it. This little part is not very big. If we do a quick little inspection here, you will see that it is only 55 millimeters from one side to the other side. And what this little part is an adapter bracket that we are going to machine from carbon fiber. And the purpose of this bracket is it takes the bolt pattern on the outside here, which is your standard servos, and I'll show you a couple of servos just now. This is your standard servo bolt pattern on the outside, and I'm adapting down to a little micro servo bolt pattern on the inside. And the reason I'm doing this is there's very limited space inside this little 1/10th scale carbon fiber car. It is a Tamiya TT02 chassis, but a full carbon fiber one. And I need all the space that I can possibly have available to me for the electronic speed control, the motor, and the batteries. Because I want to push this little car to get to 300 kilometers per hour, I need all the available real estate for power management. If you want to go fast, it's all about the power. Okay. So this little part, I already have my setup done for this, and it has two little machining operations. If we run the simulation on this, we will see what this part looks like when it gets machined. Okay, there's the one hole, there's the other hole. Those are little boring operations. And then we do the center pocket, and we do a 2D contour all the way around. And that is it. That will be our machining op. 2 operations. One is ball. We can look at that again. Slow this down a little bit. This is closer to real speed. The yellows are your lead ins and your lead outs. The blue is the actual motion. We can go right in there. The blue is the actual circular pattern, the motion. And right in there, that's what that little 2-point-something milling bit, 2-point-something millimeters milling bit will actually do. All of this will be done underwater. You do not want to inhale carbon fiber dust. That would be a very bad experience and potentially could lead to long-term damage to your lungs and your respiratory system. So we want to avoid that and stay healthy. And I will show you the setup that I do for machining this part underwater very safely. No need for any respiratory protection, no need for a vacuum cleaner, nothing like that. Okay. So that's our part. We can exit the simulation. I just did a little render here in carbon because it is a carbon part that I'm making. And this is what the part looks like in CAD-CAM. Okay. So from here, we are going to step over to the milling machine. Okay, so this right here is my Omeo desktop CNC router / mill. These types of machines are generally more considered to be routers rather than CNC mills. This one has been through the ringer. I have made many parts on this. The original bed I replaced with this super thick solid piece of 6061 aluminium, and it is a very big working surface on this machine. Okay, so what we have here is we have a piece of carbon fiber that is fixtured down with blue painter's tape and super glue. Super glue actually works really well as a fixturing mechanism for this type of work. You can actually fixture down aluminium and even titanium parts with blue painter's tape and super glue. Okay, so this is the little tip that we are going to use to mold this part. It is coated with a titanium, it's called a nano coating, I believe, and this is the type of tips that is very well used for machining PC boards, glass fiber, carbon fiber, any of that type of material. Okay, so I'm not going to do a deep dive on this machine, the details about it. I will do that in a later video. There's significant upgrades to come to this machine, but for now we are just going to look at the milling of the part underwater. We're going to look at the final product and what it is intended for. Okay, so this right here is Mach 3. This is the program that I use. Again, even for this, I am not going to go into a lot of detail on this because I am going to move away from this system. But what I'm doing here is I'm loading the postcode, and as you can see over there, it says Savox adapter up over there. This is the part. This is the main page for Mach 3. Here's all the different X, Y, Z and 4th axis machine coordinates, the feed rates on the machine, spindle speeds, all of those things. Now that I have loaded the program, I have a little toolpath over there. We can take a bit better look at that. There's the little toolpath displayed on the machine. So what I need to do now is I need to tell this machine where on this bed I want it to cut that part. So I need to give it a X, a Y, and a Z axis 0 position so that it knows exactly relative to the carbon fiber part, the stock, where the tip of this tool is in 3 axes so that it knows exactly where to start and where to stop cutting. Okay, so this right here is my wireless Bluetooth controller for my machine, and this is what I use instead of a normal fixed hand pendant system to jog my machine. And with this, I will now guide the tip of my tool down to this piece of carbon fiber to where I want to set my X, Y, and Z height for this to start cutting the profile of the part that I want. Okay. Okay, so let me take you through that process again. We're going to go to load G-code. We're going to go to desktop, postcode out of Fusion over there, Savox adapter.tap file. That's what my machine reads on postcode. There the file is loading, and now I'm going to home the machine, and then I'm going to zero the offsets for the part. Okay, so what you're going to see here is just the machine doing a homing operation. It teaches itself its own 0 offsets again. Z0. Y0. And as it's doing this, you will see on the program the X, Y, and Z axis values change. Okay, so those are all my machine home coordinates. Okay, so now that our machine is zeroed, we are going to go ahead and we are going to do a work offset for the part. Okay, so I know exactly where the machine is going to start cutting, and I will show you that again on Fusion. It's going to start cutting on the top right hand corner. That's X positive, Y positive, Z negative, Z positive. Okay, so judging by what I know about the part I want to make, I want to start somewhere around here. I try to always fit as many possible parts into a piece of carbon fiber so that my wastage is as little as possible. Once I have touched off the tip of the tool on the top of the workpiece to set my tool height 0, I will only then fill this tub with water. If I fill it with water now, I will not be able to accurately see when I touch off on the top of the workpiece to judge my Z height offset. Okay, so here we go. I'm doing all of this kind of by eye. I know that I want to start somewhere around there. The only measurement that I want to be truly accurate is my Z height. So now I changed the increments. It's 1 centimeter. Now I go to 0.1 millimeter steps until I touch the top of the work. Okay, there I can hear and feel that the tip of the cutter is ever so slightly touching the top of the workpiece, so that is going to be Z0. So now simply go to Z0, and when I press this, that enters the Z0 offset for the work in the machine, and I'm going to go Z0, Y0 and X0, and now if we look on the screen over there, we will see X, Y and Z are all three zeroed. My fourth axis is always zeroed, it's not connected at the moment. And now the machine knows exactly where X, Y and Z0 is in the workspace for it to start machining. Okay, let's fill this bad boy up with water. Now I can step away, I can go back. I can step this away because the machine now knows exactly where that workpiece is. It is programmed. In goes the water. Okay, fantastic. If I added all of this water beforehand, as you can see here now, it would have been very difficult for me to judge accurately when I'm touching the top of the workpiece. Okay. Next up, we are going to go cycle start, and we will run this file. Okay, so I'm running this at ×2 speed here, just so that we can get through this a little bit quicker. You'll see the water gets really murky and black real quick. So what I do is I listen to the cutting tool, I listen to the spindle, I watch the parameters on the PC, and after a while, once you get used to this, you kind of know what good sounds like and what bad sounds like. So you just keep an ear on it. I'll just show you some of the parameters here. As we're running on the left, that's how we're running through the G code, and on the right you can see the coordinates change. Just change the angle here a little bit. Get that out of the way. Now you can see that little carbon dust cloud forming in the water. I prefer that in the water and not in the air and not in my vacuum cleaner either. It's just safer and easier doing it this way. It spares you a lot of hassle of trying to make sure that your vacuum cleaner catches all of that, or you need to wear respiratory protection. So yeah, I prefer this method. It works really well for me. I've done this right from the start. I've learned this from a couple of other YouTubers. Here you can see it's still running through the code. And pretty soon we're going to approach the end of this file. It's not a very big file. This is a quick cut. I did not look at the runtime beforehand. But yeah, and I think we're going to come up on the end of it right about now. There we go. It's going to go to a safe retraction distance, it's going to switch off the spindle, and it's going to go to home position. And there we go. Okay, so let me get you a little bit closer in so you can see all the carbon fiber dust that is now trapped in the water. It's actually quite amazing to see how the cloud of dust forms as it spreads through the water. Okay, let's get a look at that carbon fiber cloud in the water here. All of this dust you would have needed to capture through either an extraction, a ventilation system. You would have to wear a really good mask to help you to not breathe any of this. But when you cut underwater, that solves all of your problems. Okay, so let's go fishing and find our part in there. Okay, it's a very, very murky water in here. And there is our pot. And it came out beautifully. Now I'm going to clean this up underwater with a little bit of sanding paper. And then we will look at where this pot goes and how this is going to help that poor little 1/10 scale Tamiya TTO2 carbon fiber car go 300 kilometers an hour. Okay, so here we have the poor victim of all of this experimentation. The problem when you try to make these RC cars go ridiculously fast is weight, power, and area. If you do not have enough space, if you don't have enough real estate under the body of this car, you cannot fit a motor big enough, a battery big enough, and an electronic speed controller big enough to get you to where you want to go. So the motor that I've got in here now is not the motor that this car will ultimately run 300 k's an hour on. This is a 6S capable 3000 some odd kV rating motor, and all of this is just for initial testing, for getting the gearing sorted. This is a 3660, it's a 3660 can, and it's a 2600 kV motor, meaning for each volt on the battery, that motor will spin 2600 RPM. Okay. My battery has to sit on this side, and I still have to modify quite a few things on this side. On this side of the car, I have to fit the motor, the electronic speed controller, and the servo. The electronic speed control I'm starting off with is a 6S capable ESC that I scavenged out of a low C 3XLE. Victim number 2. This speed controller I can get to fit here just barely. It slides in underneath that little piece of carbon there, if I got it the right way around, and then it sits extremely tightly and closely up against the motor. Okay, there we have it. That's where I can wedge the ESC in. It sits flush with the outside of the body. This little carbon ear over here, I still need to cut that off. I will machine that off. So enter the problem for which we just machined this solution. So there's our little part. It came out beautifully after cleanup. I had a quick measure on it. Everything seems to be good. That is a beautiful little carbon fiber part that we all just made together. Okay, this standard car over here takes a standard size servo. I love my Savox servos. This little servo will break if I do that with it. Fortunately, these servos are bulletproof. If you see what we do with them, you'll understand. Okay, so this servo will go in there. It will bolt up to that standard servo bolt pattern mounting bracket that it has over there. But here's the problem. I need to now go at least 7-8 more millimeters to close that gap but my servo is already up against the speed controller. There is no way I can fit this standard size 8th scale servo to this car anymore. Hence why we just made that little part. We can throw that out, and now we have this little Savox micro servo, and I absolutely love these. And let me show you how this fits into the little bracket that we just made. Okay, we put our power wire through there. And there we go. Beautiful fitment. Our servo sits inside the little bracket. And now this will mount up onto the standard bolt pattern for the standard servo over there, and all our clearance problems is solved. We can add a even bigger electronic speed controller here now without any difficulty. This little servo might technically be a little underpowered for what we are trying to do here, but when you do high-speed runs, you actually are not looking for extreme steering angles. You're looking for very small steering adjustments. So I can put a very short little servo horn on here to maximize the torque output on this little micro servo, because I don't actually need the wheels to turn massively. At 200 plus k's an hour on these cars, you actually need very little steering correction. So I can compromise on steering amplitude by putting on a shorter little servo horn over here and ensure that this little micro servo will do what I need it to do. And we've just saved all of that space, and now everything fits. I can now basically do electronics on this car, wire up everything, put a battery on here, and it should be ready for its first blast. I do not know what the diff ratios in here is, so I cannot calculate final drive, so I actually don't know how fast this will go even on a 6S setup. So the only way to find out is to run it. Okay, so that will definitely come up in a future video. Okay, so I thought it would just be a good shot to show you guys side by side the comparison, the difference between these servos. So that is all of the real estate that we have now gained by going to a micro servo, and we can now fit more underneath the hood of this little car. And our little carbon fiber bracket came out beautifully. These cutting end mills for PCBs and carbon fiber really work well. A lot of you might ask, why do I have these radiuses in the corners? It's because a round end mill cannot cut a 90-degree perfect square angle like you have on the corners of your parts, like the servo over here. So you have to do a little relief cut in that corner to make sure that that perfect square fits into there. Okay.
Okay guys, that is it for today's short little episode. I hope you guys learned something new. If you've got any questions, please post them in the comment section. If this is the type of content that you like, that you would like to see more of, we're going to go into hardcore development of these poor little RC cars. I need to send them to the moon. Please comment, post your questions. I will try to answer everything. Like I said before, I am not an expert at any of these. I am just enjoying myself, and I'm bringing you guys along on the journey. So if you like this content, please subscribe. Please click the bell and make sure you get a notification every time I upload a new video. Thank you very much.